Hi, welcome to Chapter 3, Understanding and Appreciating the Time Value of Money. So this chapter should really be a review for you because time value of money should have been covered in at least 2 or 3 other courses before you've taken this course. So you may have had it in finance or principles of finance or financial accounting or introduction to business. Um, it's covered in a number of classes. So this is really just going to be a review for this chapter, and I also have an Excel spreadsheet I'm going to go over with you as well. Now, in this chapter, we're going to talk about compounding, the power of time, calculating present value of money, calculating annuity, calculating future value, comparing money for different time periods, talking about a dollar received today compared to a dollar received in the future, and how is this involved with personal finance. Now, first thing that we need to cover is compound interest. So compound interest is earning interest on your interest. So it's reinvesting your interest in your principal, and then next time you get interest, you're getting interest on a bigger principal amount because you reinvested in your principal. So when we say principal, that's the face value, the deposit value of your savings vehicle, whether it's a savings account or a bond or debt fund. Now, there's 2 terms, future value and present value, and they're actually reciprocals of each other. Now, future value will equal present value times the amount of the present value, and it increased by the end of the year plus I. So we're going to go over these formulas, and I'm going to show you a really easy way to do it in Excel. But future value is basically the value of the money in the future, and present value is the value of the money today. Now, annual compounding is when interest is given once a year. So that's a pretty most easy calculations is annual compounding. So that would mean that the number of periods equal the number of years. Now, N is usually what we look at as the permutations on compounding. So annual compounding, N will always equal the number of years, but only in the annual sense. Now, here's some compounded interest over time. So here we have, if we look at the red area here, this is the interest earned on a $100 deposit. And the blue area is the interest earned on interest. And the green area is the original $100. So here, if we're earning $6, it's a 6% rate of interest. So the next year, we're going to earn another $6 for the interest on the $100 plus 36 cents for the interest on the interest. So as time goes by in 10 years, you can see that the blue bar probably grows the fastest, even though the red bar is the biggest, but the percentage growth is biggest in this blue bar, the interest on the interest. And this is how the compounding works. Now, the future value interest factor, this is the rate that we multiply the money against to get the future value. So it would be the present value times the factor to get the future value. So here's a chart of the factors. Now this is old school, where before we had calculators, before we had financial calculators, before we had computers, and before we had Excel, we used these clunky charts to get the factor to multiply against the money. This is no longer relevant or needed anymore. This is just really old school, very old school technology, is this paper chart of calculating the interest rate times the periods to get the factor. Now, the rule of 72 is pretty important. How long for your money to double? So if you want to know how long it takes your money to double, you want to divide the interest annual growth by the interest rate of 72. So, and you want these whole numbers, don't keep them decimal. So if you had a 9% return, you divide 72 by 9 and your money should double in 8 years. Now, compounding could be annually, it could be quarterly, it could be monthly, it could be daily, or it could be continuous. So money grows faster in the smaller compounding period. So if you're compounding daily, you'll have more money at the end of the year than if you're compounding at a 6% annual rate. So the frequency of compounding really grows the money faster. That's why you're typically, when you have a loan, your loan is typically compounded monthly. If you have a savings account, it's typically compounded quarterly. And if you have a bond, it might be compounded semi-annually. Now, there are plenty of time value of money financial calculators that you can easily work with. There's one in my finance lab. Now, financial calculators are, again, this is kind of old school. People don't really work with financial calculators in the uh, real world work environment. They work with Excel. So I'm going to go through Excel in a minute to show you how to calculate these problems. But the book will cover things using a financial calculator, which you could use either. The financial calculator is easy, but Excel is a lot more versatile and a lot easier to do multiple problems with, because once you set the formula up, you could just change the numbers using Excel and get new answers. Now, if you look at compounding over time, here we have 20,000 compounded over, I guess this is 30 years. What are they saying here? Contributes 1 through 10 years, years invested 10, compounded 20, total invested 20,000 here. Compounding years 11 through 35, years invested 25, total investment 50,000. So um, what this chart is showing that if you invest 20,000 and you're contributing in the first 10 years, the compounding return at the end of 35 years will be much larger than if you started in year 11. So the first 10 years you didn't contribute anything. Then you did your contributions between years 11 and 35. So your total compounding years, total invested years is 25, but you're only going to receive 146,000, because it's very important. The sooner you start investing, the bigger your compounding returns. That's why when you want to save for retirement, you should start the first year you're working, not the 11th year working, because you'll get much bigger returns because you have time on your side. So that's kind of trying to represent that. Um, so the interest rate is going to be one of the most critical factors in how fast your money grows, and the higher the interest rate, the higher the bigger the compounding, the higher amount of returns at the end of the day. So if you did a daily double, meaning that you had 100% compounding rate and you started with a penny, so every year your money doubles basically. So 1, 2, 4, 6, 8, 16, 32, $64. By year 31, you'd have 10 million. So if you take a penny and you double it at 100%, 100% basically interest rate or compound rate, you'd have $10,737,000 after 31 years. So just show you how powerful compounding can be. Now, a big problem or a big fear in a lot of marriages is, will you have enough money to retire? And 66% of Americans don't understand the concept of time value of money. And understanding compound interest and time value of money will help you to really um, understand how much money you'll have over a certain lifetime of investing. So present value. This is looking at basically, if you have future money, what is the value of that money today? So if you take away the inflation, it's sort of like an inverse compounding. That's why the present value and future value formulas are inverse of each other. So the discount rate is another term for interest rate, but when we do time value money present value, we're always saying discount rate because the money is being discounted or made smaller. So again, we have a formula where we take, um, we want to take the future value amount and decrease it by the present value factor. And then we can simply do that by taking the future value, multiplying it by the present value factor. And we have a separate chart for the present value factor. And again, really nobody's using these charts anymore today, but this book is probably written by an older academic who is carrying forward these older calculation ideas. In this class, I'm going to show you how to do it in Excel, which is really how the business world does it today. Now here's an example. You're on vacation in Florida and you see an investment stating you will receive $100 simply by taking a tour of the condominium. So you discover that the $100 is in the form of a savings bond, which will not give you the $100 for 10 years. So what is the present value of the $100 received in 10 years? From today at your discount rate at 6%. So, uh, so if you put that in a present value formula, you'd find that the value of that money is much less in actual money today than it would be in 10 years from now. And we'll calculate this later. So an annuity is another type of present value problem. We're not talking about a single sum, but a series of cash flows over a specific period of time. So annuities get compounded along with the additional cash flow. You get compounding. So the money grows really fast because you're getting additional inflows of cash periodically plus um, interest. So this would be more like saving for retirement. And so if you had you're investing $500 each period, so you go from you know as you're investing each of those $500, you're also getting interest on it. So the $500 invested in last year has no interest, but the year before has some interest, and the one 5 years ago has the most interest. So your total savings, instead of being the 2,500, it would be if you just had a 0% interest rate, and a 6% interest rate is 2818. So we could calculate these future values of annuities using another factor. This is a different chart with the annuity factors. Um, Okay. You can also do a present value of annuity. So if you're going to receive $1,000 a year for the next 10 years, what's the value of that today? So again, we have these present value factors, but we have to discount the money because the money in year 5 is worth less in today's terms due to the discounting, which is really representing like an inflational or opportunity cost. So instead of getting the full 2,500, it's really only worth $2,100 today because of the discounting. And we have an annuity factor as well for those present values. Now, amortizing a loan, so if you take a loan, say you borrow $16,000, you're going to be paying back that $16,000 plus interest over time. So this is something when you calculate the annuity payments, um, it's sort of like amortizing a loan. So your loan's made up as principal and interest. And the beginning of your loan is made up of much less principal and more interest in the beginning of the loan because you have a bigger balance. And as your principal balance is smaller, your interest is less and your principal is bigger, and then keeping a steady payment of the loan throughout this time period. Now, perpetuities would be a rare type of present value problem where you're going to be provided some sort of dividend forever. So perpetuity just means forever. So if a contract or something says in perpetuity, it means you're going to receive something forever. So in summary of this lecture, basically time value money is how we calculate the compounding interest. And the future value of money will show you the growth of this money over time. And the interest rate is going to be your compounding rate. And present value is sort of moving the money backwards in time. So it's sort of reverse compounding, where we're looking at a periodic of payments, but we're adjusting it for uh, the discounting of money and inflation and bringing it back to the present value. Okay, so let's look at this in terms of Excel. So I'm going to use Excel here. Let me get this up though. Okay, so here's an Excel document that I'm going to load onto the course management system so you can easily get this file when you're ready. And what we're going to do is we're going to calculate some of these formulas using Excel. So you learn how to use Excel to calculate these formulas. So this is the time value money future value. So basically it says if you have a present value of $100, and present values are always expressed as negatives. This is how Excel works. And we're going to invest it for 3 years at an annual rate of 10%. So here in the file, I have a little note saying use the FV function. If I go to formulas and I go insert function, and I'm going to look for I'm going to search for FV, which is future value, and I click on that. So now the rate is going to be the annual rate The n per is the number of periods is 3 because it's annual, and then the present value is going to be the present value here. So I hit OK, and that's going to give me $133. So let's try it again on example 3. So if I want to use that future value again, I can just take the rate, the n per, and the present value. So these are the three inputs, and I get, so this would be the $1,200 would be $1,800 after 4 years with a 12% rate. And this is the same, you would use the same formula in problems 2 and 4, which you could try on your own. Now, if we're going to do a problem where we have a different type of compounding semi-annually, so when we calculate this, we have to take into fact that the rate, the annual rate, should be divided by the compounding. And the n per would be multiplied by the compounding. And this is to denote that it's compounding twice a year. So I have to divide the rate and multiply the periods. And then put the present value in there, it's the same present value, and we can calculate, and this will calculate the future value based on semi-annual compounding, which is 2. Quarterly would be 4, monthly would be 12. Okay, so if we're going to do a annuity, we're gonna have to do we could use the future value still. So we're going to put in the rate. This is annual rate. The n per, since it's annual, just 5. And instead of using present value, we're going to use payment because annuity is a cash flow. So we're going to put in payments. So we'll go to payments, and we'll see here that this 250, given that we're putting $250 in every year for 5 years at a 10% rate, grows to $1,526 because that would be annuity payment. So the big change here when we're calculating an annuity for future value of annuity, we're going to use the payment field instead of the present value field. So and again, the frequency annual is 1, semi is 2, quarterly, monthly, daily. So here we're going to do the annual deposits amount to accumulate to a future sum. So if we want to get $4,000 in the future, and we have 4 years to do it at a rate of annual rate of 8%, how much would we have to save each year? So here we have a note to use the payment function. So we're going to go in here and use the PMT. This is the payment function, and the rate is 8%. The n per is 4, and the future value is 4,000. So if I calculate this, it'll tell me that I'll need to save $887 a year. And it's negative because it's a negative cash flow because you're taking things out of your money to save for this project. And this is how much I have to save to get to 4,000 with this. If you don't like this negative amount, you could just put a negative value in front of future value if you wanted to make this positive. Now let's switch over to the present value. So here in present value, make this bigger. Okay. Again, this present value is the opposite of future value. So what we're going to do here is, when we calculate it, we're going to use the PV, or the present value function. So the rate, of course, is the rate. N per, it's an annual, so it would be the same as the years. And then we'd put in the future value. So how much is $100? If we're going to receive $100 3 years in the future at 10%, what's the value of that today? $75. And again, present value is going to express as a negative. If you don't like that negative being expressed, you can put a negative sign in front of the future value to convert that to a positive number. Because really the present value should be a positive number. It's just the way Excel expresses it. Now if we're going to do this again as the same example, we just put in our rate, our n per, and then the future value. And again, if I want to I can put a negative sign there. Because all answers in time value money should be a positive answer. So you can kind of easily convert that to a whole number that way. Now, if we're going to do semi-annual compounding, Here, again, when we use the present value, we're going to take the annual rate and we're going to divide it by, just like we do in future value, divide it by the compounding. And we take the n per, and just like in the future value problems, we're going to multiply it by the compounding. And then we're going to input the future value, put a negative there first, so it expresses as positive, and then we're going to get the future value amount of this problem where the compounding is semi-annually. Sorry, the present value amount. We're calculating present value. Now, what if we had a present value of annuity? So this is an annuity, meaning we're going to get there's going to be $1,200 payments every year for 3 years at a 10% rate. So if someone's going to give us $1,200 every year for the next 3 years at a 12% discount, what's the value of that today? As if someone was going to give us a lump sum today, what would be equal to this annuity? So again, we're going to use the present value. We're going to put in the rate. We're going to put in the years, but we're going to use payment first. And we put a negative in so it expresses as a positive amount, and done. So this would be the present value. And you see that $1,200 a year for 3 years would be $3,600, but here's only $2,900 because we're discounting at a 10% rate. So $3,600 in 3 payments is really only worth $2,900 today at this rate of discounting. So how much, if we want to calculate the annual loan payment, so if we're going to borrow, say we borrow $6,000 that we're going to pay back over for 4 years at 12% rate, what is the payment going to be, the annual payment? So again, we're going to use the payment function. So we have the rate, we have the n per, and then we have the present value of what we're borrowing. So that would equal, we'd have to pay $1,975 each year for 4 years to pay back that loan. Okay. Now, let's just look at a couple of the things in this spreadsheet. There's a retirement calculation in the spreadsheet, something that we're going to cover when we do our retirement chapter. Here we could calculate, if we want to calculate the car loan and home loan. Say you're gonna buy a $26,000 car. That's going to be a 5% rate of interest for 5 years, and it's going to be a 12 monthly payment. How do you calculate the value of that loan? Okay, so if we want to calculate a loan, we're going to have to do the payment function. So we have the rate of 5%, but we're going to have to divide that by the frequency, the monthly frequency. And then we have the n per 5 years, and we're going to multiply that by the monthly frequency. And then we have the present value, I'm going to make that negative, of $26,000 because that's the money they're giving us today to buy the car. So this loan would be $490 per year. So that would be the payment of the loan. So what if you're going to buy a $426,000 house at a 4% rate of interest? How much would that cost you? So again, this is a payment function. So we're going to buy a house at 4% interest rate that we're going to have to divide by 12 months, and then we're going to have 30 years to pay it off, and we have to multiply that by 12 months because we're monthly, and then we're going to have a present value of the loan of $426,000. So the loan payment, and I'm going to make this, again, this should be negative, and this means the loan payment, oops, what happened here? Oh, I had to put it under, it should be present value. There we go. I think I had an extra space in there. And it's $1,912 would be the mortgage payment. Okay. Now, something else that we're going to talk about is this is going to come up in, okay, so this page is the EPR and the EAR. So what we're talking about here, becomes more important when we do our credit card chapter, but this is what we call the nominal annual rate of interest, or the APR. This is just the stated flat annual rate of interest. But since nobody really compounds annually, the effective EAR's effective annual rate, uh, so if we're going to calculate this, we have this formula called effect. So what we're going to do is we're going to search for effect as a formula, and then we're going to put in the nominal rate. So here's the nominal rate, and what's called N peri, and this is the frequency. So you see that 8% compounded annually is 8%. But what if we take 8% and we compound it semi-annually? And what if we take 8% and we compound it quarterly? And what if we take 8% and we compound it monthly? So you see that the effective rate is much higher. So that way, truth in advertising, if they're going to give you the annual rate, the nominal rate, they have to also show the effective rate, especially for loans. So you know what you're actually really paying when they put in the compounding effect. So I just wanted to kind of go over that with you. Okay, so last thing I want to talk about is rates and period. If you ever had to calculate the rate, there is a rate formula that you could use. So you put in your N per, you put in this case, we're going to put in our present value, which should be negative. We're going to put in our future value, and this will tell us our rate of interest. So very simple to calculate. I'll do it again. Use the rate function, use your N per, and then we use our present value and our future value, and this will tell us what the rate of the loan is. So that's how you can easily calculate rate. Now, if you needed to calculate the number of periods, or the N per, there's a formula called N per that we could use to calculate the number of periods. So here we would put in the rate, and then we would put in the present value and the future value. And it calculates the number of years. So this would be 11.91. And it's just algebra. We have one missing variable, so we use the other 2 or 3 variables to calculate the missing variable. So that's the last thing I wanted to go over. Okay, so this, what I went over in this spreadsheet basically covers what the chapter talks about in calculating present value of annuity, future value of annuity, calculating present and future value with different compounding rates of, say, monthly, quarterly, semi-annually, looking at the period and how to calculate the periods, how to calculate the rates, how to calculate the effective annual rate. Um, so this is, again, this chapter should just really be a review for you, and it's important for me to go over it again, even though you most likely had it before, but I just wanted to review it quickly because it's stuff that we're going to use in future chapters when we're calculating loans, when we're talking about credit cards, when we're talking about investments. So these concepts are going to be embedded in a few future chapters in this book. So I just want to make sure that our bases were covered, and I just gave you a overview of time value of money, just to refresh it in your memory and then show you the best way of calculating it is definitely using Excel. So practice with this spreadsheet and try to calculate some of these same calculations I made in the spreadsheet. There are other worksheets in the spreadsheet that we are going to most likely cover in different chapters when we get to our loan and credit card or investment chapters. Okay, thank you for your time today, and I hope you found this educational. Take care.